There we go. All right. So last time, when we were all together, we started talking about alkanes, also known as hydrocarbons. And I told you all that you were going to be responsible for knowing the first 10, right? So an alkane with 10 carbons is decane. 5 carbons is?
Pentane.
4 carbons is?
Butane.
All right, very good. That's good enough. Right? So we got methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Anything after that, I will tell you the formula. So what do I mean here? I mean, on an exam, it would be perfectly legitimate for me to say something like, which of the following is the structure or the molecular formula of decane? And you'd have to...
Decane would be the C10H22.
That's right.
Do we need to know the condensed structural formula as well, or just the
You will be able to get if you can do the line structure, you'll be able to get the condensed structure. You need to know all of those pieces, yeah. So, there's a way in which you can name alkanes. The good thing about this class is we're not going to go into a lot of nomenclature, but you need to know a little bit, okay? So, nomenclature is actually pretty easy for things up to 10 carbons, but there are some rules that you have to follow. These rules are just the way it is. You've got to know the rules. Okay? Nomenclature, yep. It's how we name things. That's what nomenclature
And I
means.
was saying, when did we step into biology?
No, we haven't stepped into biology. Nomenclature doesn't belong to biology or chemistry. It's just a word. Okay? There are 3 parts to every name of an alkane. There's a prefix, there's a parent, and there's a suffix. When we name organic molecules, there will always be a prefix, a parent, and a suffix. Okay? The prefix tells us what's attached to the parent. We call those substituents. Okay? The parent is going to be the longest continuous carbon chain. You'll see examples of this in just a moment. Okay? Don't panic. And the suffix tells us the functional group. Okay? Alkanes are a functional group. It's not part of the list of functional groups we learned earlier because the only function it has is you can burn them. Okay? You can oxidize alkanes. That's about all you can do with them. Okay? The suffix for all alkanes will be ane. How convenient is that? Alkane, A-N-E, tells you that you're dealing with the alkane functional group. Okay? So, this can get complicated. You will probably have some examples in your book that will be complicated. I am not going to throw a ton of nomenclature at you on an exam. There will be a little bit, okay? But got to be able to do these things. Identify the parent, find out what the prefix is and the suffix, okay? So let's go through that. The things that are attached to the parent, okay, we call alkyl groups. Alkyl groups. Okay, so let's look at an example. Well, let's look at this one. All right, there's our structure. What's the longest continuous carbon chain? 4. Right? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. So 4 is the longest, right? Right? I can either have a 3 chain, I can have a 4 chain, or I can have a 4 chain. So 4 is the longest continuous chain. Once you have found the longest continuous chain, this is a Doug Masterson tip, circle it. You'll notice I like circles. What's in the circle?
Parent chain.
The parent. And the parent has 4 carbons. So what's the parent? Butane. This is a butane molecule. Okay? So the parent is but, not but. But. Okay? Now, according to the naming, I got to figure out what my prefix is and my suffix. The suffix is pretty easy, right? It's an alkane. Okay, now I got to figure out what my prefix is. What's my prefix? It's what's attached to the parent.
Hydrogen CH3.
A CH3, that's all that's attached, right?
Oh.
CH3 is one carbon atom, so it's going to be a methyl group. It looks like methane minus one hydrogen, it's a methyl. So this is methylbutane. Okay? We found the parent, we identified the prefix and the suffix. This is a very simple example. We're going to work some more. Okay? Now, what if it had been, well, I don't want to get into that yet. All right? But what you notice is all of your alkyl groups will just be the alkanes that you learned minus the A and E ending. You just add YL, right? So methyl butane, right? CH3, it's got one carbon atom. Okay? So that's what we do. Once the carbon substituents bond the longest carbon chain, those are called alkyl groups. So what if we had something that looked like this? I would have another methyl group, right? I'd have two methyl groups, and I'd have to figure out how to put all that out here, right? And we'll talk a little bit about that, okay? Naming an alkyl group is just as easy as it can be. All you do is find the number of carbons, you drop the A and E ending, and you add YL. Okay, so for example, if it's methane, it becomes methyl. If it's ethane, it becomes ethyl. If it's propane, it becomes, if it's butane, it becomes, okay. And if you get much bigger than that, they start to become part of the parent. You don't really worry too much about it, okay? As you can imagine, since organic molecules can get quite long, these names can get really hairy really quick.
I've noticed that a little further, yeah, they get
Yeah, and we're not going to deal with the really hairy ones, okay? We're going to keep it pretty straightforward. So if you look at my example there on the screen, right? You see that I have the longest parent chain listed in green. What's the parent? How many carbons are there? 10. So this is a decane. Yeah, it's deca, right. So decane, right? So it's a decane molecule. The molecule, or the piece, so if I circle that, right? The piece that's in purple, how many carbons are that? 2. So it's an ethyl group. And the yellow one? 1. It's a methyl group. So this is a ethyl-methyl decane of some type. Okay? Notice we haven't started putting numbers yet. You don't really know where the ethyl is in terms of how I'm telling you, but we got to figure that out as well, right? Okay? So, again, thinking about how we can name the alkyl group. So imagine you've got 3 carbons, right? We've got primary hydrogens and we've got secondary hydrogens. If we remove one of the primary hydrogens and attach that carbon to the longest chain, we would have a propyl group. But what if I remove one of these secondary hydrogens and attach it to the longest chain? Right? So instead of, right, I could do something like this. That's a propyl group. But I could also do the same thing by connecting it that way. It's the same number of carbons, same number of hydrogens. It's just here the bond is between a primary carbon and where the primary hydrogen was removed, and here at the secondary, right? This is called an isopropyl group. So if it looks like a V, it's an isopropyl group. Where does the iso come from? What does that mean? Isomer. It's just an isomeric structure. It's just connected a little differently, okay? So you can have a propyl group and you can have a isopropyl group, okay? So let's work through some of these. Let's find the longest parent chain, okay? So if you just look at how carbons are connected, okay, you can go in any direction that you need to go to find the longest carbon chain. It's not always from left to right. It may be from left to up and from right to down or from up to down. We can draw these things any number of ways. What you have to find is the longest continuous carbon chain. What do I mean by continuous?
It means it goes on for a long time.
Okay, there's no break in it, right? That's right. It goes on for a while, okay? The way that I think about this is, and this is where writing things out matters. If I have to lift my pencil to get to another carbon, it can't be the longest continuous chain. So if I'm starting with a carbon and I'm going through the bonds and I'm trying to count them, as long as I didn't lift my pencil or pen, it might be the longest continuous chain. So here we've got an example. So you'll notice on the left and the right, it's the same carbon structure. We're not showing any of the hydrogens, so it's clear. And I could count from left to right, 1, 2, 3, 4, 5, 6, 7, 8. I could count 1, 2, 3, 4, 5, 6, 7. So that can't be the longest chain. 8 is greater than 7, right? Could I go 1, 2, 3, 4, 5, 6, 7? No. 1, 2, 3, 4, 5? No. 1, 2, 3, 4, 5, 6, 7? No. So clearly 8 is the longest chain in this. This isn't, right? 7 is never greater than 8. And so it doesn't really matter how it's written. You can bend these things. I mean, remember, these are molecules that have single bonds. We can move the atoms around. I mean, if you build a model, they don't hold still, right? We can move around on these single bonds quite a bit. And we'll build some models later this morning. So do not get in the habit of thinking you're going to read this like a book from left to right. When you see a structure, use your pen or pencil and try to find the longest continuous chain. And once you have found it, and this is the reason I like this book over the book you all have, they circle it, they highlight it. Once you have that, that's the parent, right? So what's the parent of this? If it's 8 carbons, it's octane, right? And what's this alkyl group? Methyl. What's this one? And what's this one? Ethyl. Right. Very good. Okay. Sometimes you will run into situations where no matter how you count, you're going to have 2 chains that are of equal length. When that situation arises, always select the chain with the more substituents. It's just the rule. All right? So if you look at this, I could count, right? 1, 2, 3, 4, 5, 6, 7. Or I could count 1, 2, 3, 4, 5, 6, 7. Okay? So this, if I count it this way, I would end up with a chain that only has 1 substituent on it. Whereas if I count it this way, I end up with a chain with 2 substituents. And the rule is, and why they chose this to be the rule, I don't know. But the one with the more substituent is the correct one to choose. Okay, so if you count 2 ways and you're like, both of them are 7 or both of them are 8 or both of them are 9, but this one gives me more substituents than that one, pick the one with the more substituents. So what are the substituents on this one? Methyl and ethyl. Okay, now if this happened to be correct, it's not, but let's just say this did happen to be correct. What's this substituent? Isopropyl. It's got 3 carbons, but it's connected to the middle carbon, so we call that an iso, right? So it's isopropyl. Okay? Once you start identifying things, now we have to start numbering that longest chain. Okay? We haven't put any numbers up here yet, but it's important. If I just tell you methylhexane, you don't know if that's on carbon 2, 3, or 4. You just know it's a 6-carbon chain parent with a methyl group somewhere, but it could be a lot of somewheres, right? So we got to number it. So you're going to number your longest chain in a way that gives the first substituent that you come to the lowest number. Okay? So if I started numbering from left to right, 1, 2, 3, 4, 5, 6, 7, 8, right? That means I would have a substituent on carbon number 2, a substituent on carbon number 5, and a substituent on carbon number 6, right? So the first substituent comes in at carbon number 2 here. However, if I numbered the other way, 1, 2, 3, 4, 5, 6, 7, 8, the first substituent would appear at carbon number 3. This is the incorrect numbering scheme. This is the correct numbering scheme. But it's not always left to right.
So wait, which one's correct?
This one is correct.
That one's correct, that one's wrong.
Because the first substituent that I come to, 1, 2, here if I went down this numbering, it would be on carbon number 3. You want that substituent, that first substituent, to be on the lowest numbered carbon. Okay? So, here we are, a couple of examples. So if we number this from left to right, we end up with the first substituent at carbon number 2. Here we end up with the first substituent at carbon number 2. Here we end up with the second substituent at carbon number 3, right? Here we end up with the second substituent at carbon number 4. You always want those substituents to be the lowest possible numbering system. You go until you find a difference, okay? So this is going to be correct, right? Because it gives me substituents at carbons 2, 3, and 5 versus 2, 4, and 5, okay? And they highlight the first point of, what I call the first point of difference rule. But we don't need to worry about that in this class, okay? So you're just going to want to have your substituents to be the lowest possible number that you can get it, okay? Now, if you can get the same numbers both ways, no matter how you do it, then you start to look at the alphabet. So this class requires you to be able to count to 10 and know your alphabet. Okay, so you got to be able to figure this out. So if we look at this, numbering from left to right, we've got 7 carbons. 7 carbons is what parent?
Heptane.
Pardon? Heptane, that's right. So we've got a heptane parent. We've got an ethyl substituent and we've got a methyl substituent, right? So if I number this way, I end up with an ethyl at carbon 3 and I end up with a methyl at carbon 5. If I number this way, notice that my substituents have the same exact numbers. It's on carbon 3 and 5 in both cases. But methyl is on carbon number 3 and ethyl is on carbon number 5. Which one's alphabetical? Ethyl comes before methyl, right? So I want the ethyl to be on the lowest numbered carbon. So this is the correct one. So it's going to be an ethyl methyl heptane is going to be how we're going to name this ultimately when we assign it a real name. Okay? Lots of rules that you just kind of got to know. Okay? And these are things you're going to want to keep in your notebook. Because remember, I'm going to let you have your handwritten notes on an exam. So you want to keep your notes right? Not your homework problems, but your other stuff. So
Sir, how many notes are you allowed? Like one sheet or like whatever you write?
just your notes.
Just a note?
Yeah.
You never said that.
Are you sure I didn't say that?
No, you didn't!
Oh my god.
You just said, oh, you like your notes. The entire room just erupted from ecstaticness.
Well, I apologize. Yeah, you're going to be allowed to have your handwritten notes. Because there's a lot of rules, right? There's a lot of rules. So let's go on. So you're going to name and number the substituents. Remember, the substituents for alkanes are all going to be alkyl groups, right? You have to remember that a carbon atom will either belong to the parent chain or to an alkyl group. It can't belong to both. That's why circling matters. Once I circle it, everything inside that circle is the parent. Everything outside is not the parent. Okay? Okay? Each substituent's going to need its own number. Okay? And if we have 2 or more identical substituents that are bonded to the longest chain, we're going to use some prefixes as well. Okay, so let's look at this example. I always start off by identifying the parent. We've identified the parent here, right? What is the parent?
Butane.
Butane. So it's a butane molecule. The parent, 4 carbons, A and E for the functional group. It's an alkane, so we put A and E. What are the substituents? Methyls, and I got 2 of them, right? All right. And so how am I going to number it? Am I going to number left to right or right to left?
It's the same thing.
It's the same thing either way. Right? If I number the other way, you'll notice it gives you the exact same numbers, right? So, since I have 2 methyls, am I going to write it out as methylbutane, or am I going to say something different? I'm going to call it dimethylbutane. Dimethylbutane. But that doesn't tell the whole story either, does it? Where are they located?
2 and 3.
Yep. So this is 2, 3 dash dimethylbutane. We use commas to separate numbers, and we use hyphens to separate numbers from letters. So what does this tell me? If I gave you this name, how would you draw that molecule? You would start with the parent, and you would draw the butane. You would then number the chain, 1, 2, 3, 4, and then you would add the groups where it tells you to put them. Put 1 on carbon number 2, put 1 on carbon number 3. How else could I connect that molecule? The same number of carbons, same number of hydrogens. I could do that.
Yep.
Now what's the name?
2,2-dimethylbutane.
2,2, dimethylbutane. What if I move that methyl group and put it at the end?
Becomes a pentane.
Ah, now it's no longer a butane, is it? Because the longest chain has changed to 5. So now it's a,
2.
no, it's, what's the parent?
Oh. Pentane.
Pentane. And we're
Methyl.
2-methyl. And what do we know? I know that 2,3-dimethylbutane, 2,2-dimethylbutane, and 2-methylpentane all have the same molecular formula. They're all the same number of carbons, all the same number of hydrogens. Do you have a question? Okay, all right. Models help you keep track of all this. If you can build models, it helps you keep track of it all, okay? So let's figure out what's the molecular formula. How many carbons do I have total?
Here's an answer from Encyclopedia.
Here's an answer.
6.
I got 6 total carbons. So it's C6, H what?
14.
I got 3, 6, 7, 8, 9, 10, 11, 12, 13, 14.
Oh, wait.
This is C6, H14. This is C6, H14. And this is C6, H14.
We use the formula CnHn plus 2.
Yeah. So wait, so how do you
But I was
calculate,
counting for it.
how do you calculate the H's again?
Well, I just counted them. But there is a formula in your book that talks about CN2, H2N plus 2, right? So there's 3 hydrogens here, 3 here, there's 1 there, 3 there, and 3 there. So you just got to add them up.
Put the number of bonds.
Okay, so here's some more examples. We just talked about all of this. I'm not going to spend a whole lot of time on this. Always make sure that you're separating numbers by commas and separating numbers from letters by hyphens or dashes, whatever terminology you want to use. It is important. If you wrote this out as 2,3-dimethylbutane, I would count that wrong. I can't put that into a computer and have it draw the structure. It would look at that and say, what is 23? I can't find a position 23 on a butane parent. Nomenclature is about rules. Rules are very important here, okay? Follow the rules. Very, very seldom do I say don't question the rules, but this is one of them. You just got to follow them, okay? To get the naming right. Okay, so let's look at an example. I want you all to take, let's take 3 minutes, get with your nearest partner, nearest friends. You've got the condensed formula. What I want you to do is to draw it out in bond line, like we do here. So convert the condensed into bond line, and then provide the name of that molecule. Take 3 minutes.
So what we're doing again?
Take that and make the bond line structure out of it, and then name it.
Is it okay for me to just draw the whole structure?
Yeah. Whatever works for you.
So we have to.
Yes, right. This is the result. I can walk you. So, this
Poppins is how many Poppins do you have?
You got to figure that out.
I don't feel like cleaning this up because that's a lot of columns.
It is. Yeah, I wouldn't do that here. Just try it on paper.
No, that's a lot of columns. It's 12 copies. That'll be stove deck.
so far.
So we got preparation, stove deck.
So far we got this and we can check. So you can check that this carbon,
What's the prefix for again?
it has one thing.
Your alkyl substituents.
So how?
Both of these must have.
That's not the simple version, is it?
That is the condensed version. It's there. All right, one more minute.
I thought it was myself.
It's okay.
I looked at it as like there's 12 calories there.
I think the longest.
So stove jack, that's the first prefix.
This way. 1, 2, 3, 4, 5, 6. Or you can
There's days I like bring this up, there's days I don't want to bring it up, and that's one of those days.
Let's try doing it from here. Well, let's try doing it from here.
All right. So, there is no right way or wrong way to begin these types of problems, but I'll tell you what works for me. When I see a condensed structure like that, I can't name from a condensed structure like that. I have to build it out, okay? And so when I look at it, I notice, what do I notice? I notice that there's this CH3, CH2, and there's two of them, right, that are attached to a CH. So why don't we start there? So CH, right? CH2, CH3, that's one of them. And then the other one, CH2, CH3, right? And then this is attached to a what? A CH2, and then a, and then what's attached to that? Two CH3s. Okay? Now I can build the bond line structure from that. Right? What's the longest chain? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Looks like 6 is going to be the longest chain, right? So I can start to draw that out and start to get something that looks like that. Okay? That's what the bond line structure would look like for this. I would draw the 6 carbons out first, and then I would put the groups on where I need to. Yes?
So you just can't like count how many carbons and hydrogens are in the formula?
You just counting the number of carbons and hydrogens only gives you the molecular formula, not the structure.
So you need to break it out how you did, like when you said there were 2 of the CH3, CH2, 2 of the CH.
Yeah. Build the structure. Once you know the structure, you can derive the name.
Okay, I just want to check for that first CH over there. Like you had like the CH3s, CH2s like backwards. Is it okay if we just write them like normal? Like
What do you mean I have them
CH3,
back?
CH2. Like we just write it like that instead of
Oh, yeah.
H3s.
Yeah, you can draw them like
Okay.
that if you want to. Yeah. To me, that's not backwards. But again, that's how I like to do it. Okay? So does everybody agree that's what the bond line drawing should look like?
Yeah.
Yeah, right? So now that I have the bond line drawing, 1, 2, 3, 4, 5, 6, right?
I see why you told us to study functional groups now.
Now what do we do to name them?
Find the parents.
Find the parent.
Find the parent, which is what here?
Hexane.
Yep. Now, I could have circled this one. I could have circled that one. Both would be correct. I mean, they're both the same parent, right? Okay, so we know this is going to be a hexane molecule of some type, right? What are the substituents?
There's an ethyl and a methyl.
There's an ethyl and a methyl, right? So I know this is going to be some type of ethyl methyl hexane. All right? So I can number from left to right. And if I do that, well, or I can number from right to left, right? So I've got the green numbering system, I've got the white numbering system, okay? So if I go with my green numbering system, I would end up with 3-ethyl dash 5 dash methyl hexane. Notice I placed the ethyl, you list your substituents out in alphabetical order. E comes before M. So if I go with the green numbering system, it's 3-ethyl, 5-methyl hexane. If I go with the white numbering system, it is 4-ethyl, 2-methyl hexane. And that one is correct. Why is that the correct one?
Because the lowest number.
Okay, the lowest number of what? The first substituent. I gave you this one intentionally because this confuses a lot of people. Right? They will look at this and they'll go, wait, 4-ethyl, that can't be right. 3 comes before 4. Remember, it's the first substituent that you come to. It's not where it's at in the name. So on this one, the first substituent comes at carbon number 2. Here it comes at carbon number 3. Even though when I name it, it looks like, well, 3 comes before 4. So always keep that in mind. This is one of those problems. I won't promise I'll put this one, exact one on the exam, but I always put something like this on the exam. And I never mean for it to be a trick question, and it always gets about half the students.
How do you know which one goes on the hexane?
What do you mean, how do I know which
Like,
one?
why would you not put the apple and the
I don't understand the question. I'm sorry.
Because either comes before apple.
Oh, okay.
Okay. Yeah.
So you have to make sure you count both ways before you, put the name together.
Yeah. Some of them will be obvious. This one wasn't necessarily obvious. Okay, but you have to know both ways in your numbering system to pick out the one that's going to be the most correct, right? Something about like this will be as complicated as I probably get on the exam. You will not see, 5 questions that are all the same, obviously. So, I could put different substituents. I could do that kind of thing, a little longer chain, a little shorter chain. But I'm not going to give you something that has 10 substituents and 40 carbons long or anything like that.
So if you reverse that and put the ethyl group on the 2 and the methyl on the 4, would it just swap that, be it 2 ethyl, 4 methyl? Oh.
Well, let's do it. So if we made that the ethyl and that the methyl, okay? 6 still the longest? Ah, is it? Is it?
No.
It is not anymore, is it? The longest is 1, 2, 3, 4, 5, 6, 7. So it's now a what? Heptane. And I've got 2 methyls, so it's a dimethyl. You'd have to go through and do the numbering. But notice sometimes swapping things, the chain got longer. So just because, again, same molecular formula, but moving things around. Now we went from a hexane parent to a heptane parent.
So now it'll just be 2.
It will be a dimethyl heptane. Yeah, I haven't done the numbering, but it looks like it'd be, looks like it's the same, 3,5 either way. Yeah, so this would be 3,5 dimethyl heptane. Okay? Now, cycloalkanes. So we can make alkanes and we can make cycloalkanes. Here's an example of a cycloalkane. Don't worry about the colors yet, okay? These are just hydrogens. These are 6 carbons all put together. It's easy to see why it's cyclo. It's a cycle, right? It's a ring, okay? So these rings are called cycloalkanes. Very important group of molecules. Very easy to do. You just put the word cyclo in front of the parent. So since I have 6 carbons here, this is cyclohexane. Okay? Does it have the same molecular formula as hexane?
No.
What is the difference?
The hydrogen.
The number of hydrogens. Each carbon only has 2 hydrogens, so it's CnH2n. Yep. Whereas for an acyclic alkane, it's 2n plus 2, right? For the hydrogens. So since it doesn't have the maximum number of hydrogens for the carbons, is it saturated or unsaturated?
Unsaturated.
It's unsaturated. That's right. It has 1 unit of unsaturation, okay, because of the rings. So rings give us unsaturations just like double bonds and triple bonds do, okay, which we'll learn more about later, so don't worry too much about it. Same type of thing, right? The prefix is going to tell you where the substituent or what and where the substituents are. The parent is going to tell you how many carbons are in the ring, and the suffix is going to tell you the functional group. This is an alkane. It only contains carbon and hydrogen. So this would just be called cyclohexane. Okay? But you'll notice we can put groups on there. What are the 2 substituents on this cyclohexane? Methyl and ethyl. Right? So this is some kind of ethyl-methyl cyclohexane that they have drawn up there. You just got to figure out how to number it. Okay? So, here's some examples. If I put a methyl group on this, I'd have methyl cyclohexane. Do I need to worry about a number if I just put one group on?
No.
No, because it's going to be one no matter how you number it, right? So we would just call that methyl cyclohexane. Okay? Notice we have another one here. So we have 5 carbons in the ring. That becomes cyclopentane. But notice the substituent that's attached to it. How many carbons are there? 4. So it's a butyl group. But notice it's called tert-butyl. That's because if you looked at the hydrogen on that molecule, if it was an alkane, it would be removing the tertiary hydrogen, right? And the way that I do this, it's very easy. Tert starts with what letter?
T.
And what does that look like?
T.
T. That's tert-butyl, right? So that's a tert-butyl group, okay? So now when we have a ring that has more than one substituent, we got to figure out how to number the chain. We can number the chain 2 ways. We can number clockwise or we can number counterclockwise. You always start with one of the substituents, and you start with that one at number 1. I always start at the top. So that would be 1, 2, 3, 4, 5, 6. Or I could go 1, 2, 3, 4, 5, 6. This gives me 1, 3 dimethyl cyclohexane. This gives me 1, 5 dimethyl cyclohexane. I want the lowest numbers, so that's the one on the left is going to be correct. But it doesn't have to be the one on the left always, right? It just so happens that's how we've got them built out here. You got to determine whether going clockwise or counterclockwise is the best numbering system, just like going both ways on the regular alkane that we've talked about, okay? All right. Today I brought in my big model kit, which is actually made by the same people as the little model kit. Just got bigger pieces so y'all can see it a lot easier. Okay? How many carbons do I have here? 4. So this is
Butane.
butane.
Boy, some little things that are hydrogens.
These little things are hydrogens, yeah? You can think of them as hydrogens. That's exactly right. Okay? So this is butane. What is this?
Also butane.
What is this?
Also butane.
That?
Also butane.
All right. Notice around carbon-carbon single bonds, I can rotate. Molecules have this ability to freely rotate if they're singly bound. Anybody know why?
Because it's bendy.
Because it's spindy? Is that what you said?
Yes.
Because it's a signal bond.
It's a sigma bond. And why would a sigma bond be allowed to rotate?
There's no restriction.
That's a true statement, but why does that exist that way? Pardon? Second. Don't be afraid. No?
It's weaker.
That's actually a pretty strong bond.
Is it circular?
Has something to do with circular. Yeah.
It's only attached to one point.
It's only attached at one point. You all are saying the right things. I'm not being critical here. I'm letting you go. Okay? It so happens that, yes, it's a single point. There's 2 electrons in here, right? And when I rotate it, those electrons don't change position at all. So there's free rotation around. It's not restricted around its rotation around that bond, for the most part. Okay? We call this cylindrically symmetrical. So if you look at a sigma bond, when they overlap, you can rotate around it because of its cylindrical rotation, or symmetry, excuse me. The way I like to think about it is imagine you take a sign, you put it on a telephone pole, and you put one nail in the middle. Will it stay there? Yeah, you can rotate it. It might end up upside down tomorrow, right? But what happens if you stick 2 nails in it? I can't rotate it anymore. What would be a 2 nail in this?
Double
A
bond.
double bond or a triple bond. Okay, so around sigma bonds we can rotate. Around pi bonds we cannot.
So
Easily. Let me put it to you that way.
these little things in the mind are hydrogens.
Yes, you can call them hydrogens.
Okay.
Or you can put little white spheres on them and call them hydrogens.
Gotcha.
You got little spheres in there.
Okay.
Okay.
I was just curious.
So we're going to be talking about rotation around sigma bonds. So if we build a model, right, we just built a model of an alkane, and we can see why we have sigma bonds. Now, my model kit doesn't do pi bonds very well, but imagine if we put a pi bond in there and that held it, right? Now, could I rotate? No, right? So I can rotate around single bonds, but I can't rotate easily around pi bonds, okay? And so this is the way that we can think about it. When we're rotating, we have to rotate around a sigma bond. So you have to note, tell me which bond you're rotating around. Here, we're dealing with butane. Which bond am I rotating around right now?
Between the second and third.
We're rotating around the second and third carbon. I would say, if I was telling you that, I would say you need to rotate around the C2, C3 bond. So if I grab carbon 2, if I grab carbon 3, and I can rotate around those, right? Can I rotate around carbon 1 and 2?
Yeah.
Of course I can. Yeah, I can. I can rotate around. But you need to know, right? Do we want to rotate around that bond, or do we want to rotate around that bond? Okay? Okay? So there's basically two types of bonds I can rotate around. Carbon 1, carbon 2, or carbon 2, carbon 3. Notice that carbon 4 and 3 are the same as carbons 1 and 2, so we don't have to talk about that one, right? So we can rotate. So you all told me that was butane? You all told me that was butane? If I had a magic microscope, which way do you think it would look? Do you think it would look like this, or do you think it would look like that?
Previous one.
Think it would look like that?
Because it's more realistic.
It's more realistic?
More spread out.
More
less,
spread out?
Resistance between electrons.
All right. So you're telling me that if I looked in the magic microscope, it would look like that?
Yeah.
And I wouldn't see much of that?
It would
I
look
might
like
see-
somewhere in the middle.
Might be something like that?
Somewhere in the middle, yeah, like
Somewhere
that.
in the middle between all of its isomers, or like its constitutional.
What you ever see in the book is the flat version.
The flat version. Okay. That's flat.
Okay,
That's
let
fine.
me be more specific. It won't look like the W, or the
The U?
the U won't look like
The
the
U form? Okay. It'll look more like the Z form?
or the
Zigzag.
Zigzag form?
yes.
All right. You're right. So if I went and looked in our magic microscope, which we do have, and I looked at this molecule, 99.999% of it would look like this. Almost all of it. But every now and then, I might find one that looks like that. Because it can rotate, right?
Yeah.
But if I find very little like this, and I find most of it like this, what does that tell me about the stability?
More stable.
This is more stable than this. Why? Why should this be less stable than that? Pardon? Okay, you're getting there.
Because in the U form, the two carbons are close to each other.
Ah, things start to get in the way of each other, don't they? It's hard to tell in these models, and these models actually do a pretty poor job of showing you how close things really are. These models are really good at a lot of things, but really you need what's called a space-filling model, and I can't have you go buy those because they're like $1,000. Okay, but we can build them in the computer a lot cheaper. But actually, if you built a space-filling model, what you would find is that this group and this group actually get really close to touching one another. But when they're here, they're very far apart. So when we're talking about things around bonds, you always want to get the biggest things as far apart as possible. Okay? So this is more stable than this. Okay? We call this conformational analysis. It's a conformer, not a constitution. This and this have exactly the same constitution. What do I mean by that? Okay, the same Lewis structure,
The fundamentals are the same.
the fundamentals.
Like the numbers, carbon and hydrogens. And
All my carbons are connected the same here versus here, right? Okay, but I think you all will agree that that is different than that, will you not? Okay, so they have the same constitution, that is how they're connected, but how they are in three-dimensional space is different. And so when we're talking about how things rotate around carbon-carbon single bonds, we call this conformers. So this is a different conformer than this. How many conformers about the carbon-2, carbon-3 bond do you think there are?
Just two.
Just two? Actually, it's infinity, right? It just depends on how much I move it, right? That's a different conformer. That's a different conformer. That's a different conformer. That's a different conformer. That's a different conformer, right? It's not just this or this. There's actually an infinite number, right? There's 360 degrees of rotation. So if I figure I move it every degree, there would be 360 conformers. If I move it half a degree, there would be 720 conformers, right? Now, it turns out that the way that we do this is through this thing called a Newman projection. What do I mean by projection?
It means it's broadcasting outward.
Not a bad thought.
That's the first thing it says when you say projecting.
Yeah, projecting it out. So do this on a nice sunny day. Take your model kit, build butane, go out to the night when it's like noon overhead, hold your model out, and let the sun shine and see what appears on the sidewalk. What will appear on the sidewalk? A projection of the 3-dimension. So what happens when you project a 3-dimensional structure? You get a 2-dimensional structure. That's what a Newman projection is. So a Newman projection tells us to look down a particular bond and think about how that's projected into the board. So if I took this, put this on the board, and smashed it, what would it look like? I'm taking a 3-dimensional object and I'm smashing it in.
Looking like an L.
So I'm smashing the carbon-2, carbon-3 bond, right? Well, you say it would look like an L,
Wait,
right?
hold up. Wait, you like that?
Yeah, if I took that and I smashed it, what would it look like?
It looks like it's just a straight line.
You think it would look just like a straight line? Okay, pretty close. But actually, it wouldn't be just a straight line, right? It would be, these two carbons would be on top of one another. These hydrogens would be poking out, and I'd have to draw all that, right? So the way that we do this is we draw what's called a Newman projection. So I always take the molecule and I hold the sigma bond that I want to look at the projection on. Right? So I'm holding which bond?
Between carbon-2 and 3.
Carbon-2, carbon-3. So I'm looking down the carbon-2, carbon-3 bond, right? The carbon that is in the back, we represent by a big circle. The carbon that's closest to me, I represent as a dot. Okay? That is showing these two carbons. Now there's other stuff connected to these two carbons I got to take into account, right? So what is attached to the back carbon?
Another carbon.
Another carbon, and it's going which way?
Down.
Going down. And it's a CH3, right? All right. Now this carbon has two other things attached to it. What does it have attached to it?
Hydrogens.
Two hydrogens. That's everything that's attached to that back carbon. All right, now I look at the front carbon. What's attached to it?
Hydrogens.
Hydrogens, and they're where? Down or up?
Down left, down right.
That is the Newman projection down the carbon-2, carbon-3 bond for butane. If you build your model and you go do the projection on the sidewalk, you'll see something that kind of looks like that. You won't see a big circle, right? But you'll see this as a kind of a straight line, and you'll see this coming off, that coming down, and these little things going off to the side. This is a Newman projection. What carbon is this?
The front one.
What one is this?
Back one.
This is connected to what?
The front one.
Notice it crosses the circle, but it's not bound to it. Right? So these go only to the front carbon. Right? And so why don't I draw the bond between the front carbon and the back carbon? Because when I look down it, I can't see it, can I?
Yeah.
Right? When I look straight down that, that's what I see. You all see that?
Yeah.
This is your what carbon?
Back.
This is the,
Front.
which is represented as a,
Dot.
and this is represented as a
Circle.
circle. Right. And my CH3s are, what, if you had to mathematically say how far apart those are, how would you do that? You would say that's 180 degrees away, right? So 0 degrees, 180 degrees. So if I was going to draw the Newman projection for this, how would I draw it? Just going to start off with my back circle, my front carbon. My back circle is my back carbon, right? So how would I draw the back? What's attached to the back carbon?
CH3,
CH3. What else?
2 hydrogens down where?
Now what's attached to the front carbon?
Same thing.
Same thing. And I will draw them very close to one another. Can you all see now why this is less stable than this?
Yeah.
My hydrogens are what we call eclipsing one another. If I was to do the projection, it would look like half my molecule was gone, right? Because they would eclipse, right? These hydrogens are actually very close to one another. We don't want things very close to one another. We want them as far apart as possible. This is called staggered. I think I spelled it right, okay? It's the staggered conformation. You typically want things to be in the staggered conformation as much as possible, okay? Now, not all of these have the same energy or the same stability. I used to do a model of this in the computer and show you the energy diagram. I don't really do that so much anymore because I don't have the software installed on my laptop anymore. And the software is a couple $1,000s. So anyway, this is called anti and staggered. Anti means 180 degrees apart for the biggest groups. These are anti to one another, okay? Now, which carbon are they rotating by 60 degrees? The front carbon or the back carbon, if you're looking at that? So look at this structure, right? This is what I've got right now to you, right? Well, okay. So this is the front carbon with the methyl group going down. This back carbon with the methyl group going up, that's what I've got. And they're going to rotate around this bond by 60 degrees. Which carbon are they actually moving? The front carbon or the back carbon? They're moving the back carbon, right? And they're moving it by 60 degrees. Okay? This is an eclipsed conformation. Okay? Notice how close the hydrogens are getting to one another, how close this methyl group is getting to this hydrogen, how close this hydrogen and this methyl group are getting together. So is this more stable or less stable than this?
Less stable.
Less stable. By a lot or a little? By a little bit, because hydrogens are pretty tiny. Methyl groups are bigger, right? So if I'm going to eclipse something, I want to eclipse a big thing with a small thing. Or two small things, right? That's not too bad, okay? So now I'm going to rotate another 60 degrees. Okay, now we have this. This is now staggered. If you look at that Newman projection, I think you can tell that that's staggered. But is it the same energy as the original staggered anti? Why not?
Less, the CH3s are less distance, like it's 100.
They're closer.
First time, but
Yeah. So this methyl group and this methyl group are now getting closer, right? So the energy, is that going to be higher or lower than that? It's going to come down a little bit. It's going to come down a little bit because this is eclipsed. This is not eclipsed, so it's going to come down a little bit, but it's not going to be it's not going to be as low as this. It's not going to be as stable as this.
so low is stable, like low energy is stable.
Low energy is stable, that's right. So, there we are. Now if I rotate another 60 degrees, now we have another eclipsed conformation, and my two big groups are on the same side of the world, right? They're really close to one another. So what happens to the energy now? It increases. This is the least stable conformation. Energy goes way up. Now if I rotate again, what happens to the energy?
Decreases a little bit more.
Actually increases, right? Because now I've got eclipsing a little bit. It decreased, then it increased just a little bit, and now it decreases a lot, right?
But wait, does it, okay, so when you were, go back to the first one. So here, they were eclipsing, so it was.
No, here they're eclipsing.
Here they're eclipsing, so when it moves.
So this is just a little bit more stable.
A little bit more stable.
This is a little less stable,
Why
and
is
that's
that a little less stable?
because of the eclipse.
The eclipse between which,
The hydrogen atom here and the methyl group.
yes, but would that be less than because the one before was between the carbon and the carbon.
Yeah. So this, but still not as stable as this, right?
Yeah. But
This is the lowest, this is a little higher, this is a little higher, this is the highest.
Yes.
So maybe I said that backwards to you, I didn't mean to. This is better, but, yeah, there we go. Got it? All right, good deal. Those are Newman projections. You will have to look at Newman projections. Okay, you've got some homework assignments on Newman projections. Okay, I am not going to give you tons and tons of Newman projections. Okay, but you need to understand the energy structure relationships or the stability structure relationships. Okay, because a rotation around all these sigma bonds, while we're only dealing with 4 carbons here, when you get into biochem, you're going to be talking about putting a lot of amino acids together to make a protein. There's a lot of opportunity for rotation. The rotation is important to build a structure for that protein, which is important for its function. We also have cycloalkanes that we need to think about in terms of conformational analysis. Notice I can look down any 2 carbons and I can see staggered conformations for this. Right? Look down that one. It's staggered. It's staggered, right? But notice that I have called these hydrogens, I didn't have blue and white, I had red and blue. Okay? Are these all the same hydrogen?
No, wait, no.
Well, let's think about it. What kind of hydrogens are these? Primary, secondary, or tertiary?
Tertiary?
Are they?
No, wait, no. Primary is something that's attached to the thing. Secondary is the second thing.
Okay.
Secondary.
So these are all secondary, right?
Mm-hmm.
The blue is secondary and the red is secondary.
Mm-hmm.
So why do I have them different? Why did I use different colors? Well, it turns out that these hydrogens actually are different, even though they're all secondary. Those that are red, we call axial. Notice I've got an axis that runs through here that this could rotate around, like the axis of the Earth. And these are all parallel or perpendicular to it? Parallel to it. So we call them axial hydrogens. Just like the Earth has an axis, it also has a circumference, but we call that the equator, right? So these that are blue, we call equatorial. They're around the equator of the structure. So these are axial, and these are equatorial. Okay? So we can have axial hydrogens, and we can have equatorial hydrogens, and it matters. Okay? It matters an awful lot. Okay? So you need to be able to look at this. Now, drawing cyclohexane is an art. And it is an art that I will admit to you that I have lost a little bit of my practice on. So my cyclohexanes don't look as pretty as people who draw these structures as much anymore. The fact that we have computers that do all the drawing for us now has made my artistic skills very bad. But you need to know how to draw cyclohexane. Okay? This is the way that I like to draw it. I like to start off down here and draw a little bit of a lopsided V. I draw 2 parallel lines, more or less, and then I draw another V. That is cyclohexane. We call this the chair form of cyclohexane. Doesn't that kind of look like a beach chair? There's my footrest. There's where I put my butt. There's where I put my head. Right? That is a chair form of cyclohexane. Notice, I can't rotate around the sigma bonds like I did here, But they still want to move, don't they? I can still see some movement. Watch what happens when I take my headrest and I pull it down. Now what happens to my, right? You still see that everything's staggered, right? But now look, what about these two hydrogens?
Getting close.
They're getting close to one another. Okay? And actually, if I turn it up like this, what would you call this form of cyclohexane? This is chair.
Okay.
What would you call this?
Bucket.
Bucket? Okay, close.
Table?
Table? No.
Bridge.
This is called boat cyclohexane. And these hydrogens that are pointing towards one another
The sails?
are the sails. Yeah, they're called, well, actually we call them flagpole. We call them flag hydrogens. They're flagpole hydrogens.
I could remake that with this.
You can. You absolutely can. Yep. So now, look at this. So here is a chair conformation of cyclohexane, right? I can push this footrest up and make it a headrest, and I get boat. What can I do with this over here?
Push it down.
I can push it down, and now I have another chair. But what happened with all of my hydrogens?
It's messed up.
All of the red ones went from being axial to now being equatorial, and all of the equatorial ones became axial. This is called ring flipping. And it happens. We can look in our magic microscope, and we can actually see this process happening for cyclohexane. It does this all the time. And in fact, it does it so fast that I can't really distinguish the reds from the blues very easily. But if I put a big group on here, I can actually do what we call freeze it, and it won't flip anymore. Okay? And so if I put it like a big butyl group or even a methyl group on one of these, it actually will freeze one of the conformations. Okay? We'll talk a little bit about that later as well. Drawing cyclohexane, I want you all right now, work with your partner for about 2 minutes and draw cyclohexane. Well, draw methyl cyclohexane in that form. Take 2 minutes.
We have to draw all the hydrogens too.
No, not necessarily.
So we have to turn that into that. About to make me go get a cubicle in the library. Just shut myself in.
Gotta do what you gotta do.
Oh, yeah. Trying to save money.
Was it easy to watch me draw it? Is it harder for you to draw it? Yes. And that will be the way it's going to be until you draw enough of them to where it's second nature to you. Okay? It's like anything else, you got to practice. Okay? Some of you probably got it right off the bat. Some of you have artistic skills that are better than others, and that's okay. But we can draw, again, the two chairs, right? We're going to draw that little lopsided V. We're going to draw two parallel lines kind of slanting down. And we're going to draw, there's our chairs. The methyl group is going to be on what numbered carbon?
1.
1, by definition, right? All right, and I'm going to call number 1 my headrest. Okay? So I can have the methyl group going which way? I can have it going axial, which means that there's an equatorial hydrogen there. Or I could draw it which way? I could flip it, right? Where the CH3 is here and the hydrogen is here. Now it turns out, again, that if I look in my magic microscope, you'll notice that counting them in my magic microscope, I find that 95% of them, whoops, excuse me, wrong one. I drew them opposite. 95% of it is this, and 5% of it is that. So what does that tell you? Pardon?
The one on the right more
The
stable.
one on the right is more stable. So what does that tell you though? Is methyl group bigger or smaller than hydrogen?
Bigger.
Bigger. So where do I want to put big groups on a cyclohexane?
Outward.
I always want them to be equatorial if they can be. Why is that? The reason is because we've also got hydrogens over here, don't we? And I'll draw them in like this. Draw them in like this. Okay, what do we notice? I notice that these axial hydrogens are really close to that methyl group. What about here? The methyl group's all off by its little lonesome self. This is what we call steric interference. Steric means to crowd. Do you all like to be crowded up in small spaces? Neither do atoms. So this big group is crowding these hydrogens.
So you want on the opposite side.
But here, it's not.
So essentially, you want on the opposite side of all those atoms.
Yep, essentially that's right.
Okay.
Essentially that is correct. All right, we are going to play with models a little bit on Monday. We will start getting into chapter 4 on Monday as well. So if you have a model kit, bring it. I'll try to bring some pieces. We're going to break up and play with a few models and do a little exercise in class. We have a quiz today. Turn in 2.18. 218, please. Put your name, write your ID number on it, leave it over there next to the light switches on your way out.
So, okay, when you talk about highest acids, we go from this way to this way, right?
When what?
When you go from strongest to weakest, going from weakest to strongest, you go weakest to strongest.
Right, you can do that, yep.
I did this time.
Good.
Oh, so it's even